there's a couple ways you could actually do this. There's sort of the experimental way, and then there's the using a bit of math way. Okay? So overall, the things you have to do here is you have to recognize the larger peak, the larger main peak, is something that's going to be very, very close to the entire molecule, right? And then the smaller peak is going to be its main breakpoint. Okay? So you're given some important hints here. It's a non-branching ether. So an ether is what? It's an oxygen. Yep, with 2 carbon substituents. Got it. And so you have an oxygen with 2 carbon chains on both sides, right? And then you have here a 102, right? And so you can estimate how many carbons are going to be in this if you take your ether, so 16, subtract that from 102. Okay, and that would be, what, 86, right? Subtract 2 hydrogens off there because those are your cap-ins, right? It didn't say it was cyclic, and if you are wrong and it's cyclic, you can always come back on it, right? Okay. And so that would be 84, right? And then your carbon chains are CH2s, aren't they? And so that would be 12 plus 2, 14. 6 times 14 would be your 84, right? Is that right? You want to do a calculator for me? I'm also part of that generation. Math in my head ain't so easy. Yeah? Cool. I can't believe it. So that essentially it has to have like 6 carbons, right? 1, 2, 3, 4, 5, 6 carbons, right? The only question we have now is we know we have to have 6 carbons, an oxygen in the middle, and it has to be a straight chain, right? Okay. But we don't know how many carbons have to be on each side, do we? How do we figure that out? That's the next number, isn't it? Yeah. So what we do is we take the difference between these, and that would be 29, right? Okay. And again, remember, it's going to be 14 for each CH2, plus 1 more hydrogen for the cap, right at the end. Okay? So that would be 2 carbon long, isn't it? 14 times 2. 28, plus 1 for the end. Everybody understand what I just said? And
just for curiosity, just go back through this.
okay.
Just go back through this case.
Okay. So this 102 here gives you essentially the entire chain, right? And it may be off by 1 hydrogen maybe or something like that, okay? But it's not going to be off by much, right? It's typically, on most species, especially things like ethers and such, it'll be the mass of your entire thing, okay? Okay, so it's 102, right? We're told we have an ether, which means it has an oxygen, right? We need to subtract the oxygen. That would be minus 16, right? We do that, we got 86, didn't we? Okay. If it's non-branching, and we're not given anything about it being a ring, well, what we need to do is figure out how many carbons there are, right? So in a non-branching hydrocarbon, most of the carbons are in the form of CH2s, right? Which are those methylenes. Remember our methylenes, CH2, CH2, repeated units? Okay. Each of those has a mass of 12 plus 2, right? 14. So we have to account for our 86 in terms of how many carbons, which are units, methylenes, which are 14 each, right? So we divide that by 14. And if you do 86, you're going to get a fractional number, right? You get 6 point something, okay? So you take 6 times 14, that would give you 84, wouldn't it? 2 mass units, what do you think that is? 2 hydrogens, right? That's your caps. Those are your ends, aren't they? Okay? So now we know we have 2 ends, which we should have known anyways, right? Because it's a straight chain. Has to have 2 ends, right? And we now know that we need 6 carbons to make up that mass, don't we? So there we go. The only thing we're left with now is how many carbons are on each side of that oxygen. Because it doesn't have to be even, does it? So how we figure that out is we need to take this number right here. This number right here is going to be your majority fragmentation, right? Your biggest species of fragmenting. Your biggest species of fragmenting typically is going to be on an electronegative group, right? Things like sulfurs, oxygens, just like we were talking about in the previous one, right? So we know that probably breaks on one of the sides of the oxygens, doesn't it? So if we have one side of it, we know we need a total of 6 carbons. Well, that's going to give us the other side too, isn't it? Okay. So all we have to do then is go, well, 73, the difference between 73 and 102 is what? And so what would that difference be? 29? Yeah. 29. And then we go, well, what could that be? Right? Okay, so our options are, it could be a CH3 with an oxygen, but those don't add up, do they? No. That would be 16 plus the 15, right? It would be 31. That makes sense, does it? Okay, so our only other option is, well, what about a CH3 and then a CH2? Doesn't have the oxygen in it, right? And so we go, okay, CH3, that's 15, isn't it? CH2, that's 14, that gives us 29. That's that difference, isn't it? So one side of the oxygen has a CH3, CH2, right? The other side has the remaining carbons. 1, 2, 3, 4 carbons. And of course, it has to end with a CH3, right? Like you've gotten so used to. Okay. Does anybody have any questions or got lost anywhere? Yeah, so one is just the benzene ring, C6H6. The other one actually loses a hydrogen. And you can kind of do this in 2 ways. You can figure out, well, what would happen, or you can look at the mass and go, it's 1 mass number off. The only real way to lose 1 mass number is to lose a hydrogen, right? So C6H5S, right? Then a plus. Okay. Is that okay? Right. Does anybody have any other questions or anything? All right. We'll call that good then.